start recording. Today is the 17th. This whole solving and resolving vectors thing is foundational to everything that you're going to do in physics. Pythagoras is helpful, but the solving and resolving part is absolutely foundational. So in chapter 4 and the rest of chapter 3 and chapter 4 and chapter 5 and chapter 6, were we to go there, you would need that desperately. And the reason is we deal with a lot of vectors, and what you have to be able to do almost instinctively is break out the x and y components of them. So if this is velocity on the x, this is velocity on the y. You got that? Yeah. And I didn't screw up my x and y. That's good, because sometimes I do if I'm thinking fast. If this is a displacement, if this is a displacement or a distance that was traveled, this is your delta x, this is your delta y. And you all get that, and you mostly get how to arrive at that. So now what we're going to do is something that is hideously ugly on the face, but it's actually very simple, and it rewards good bookkeeping. So if you are somebody who is really good at putting all your ducks in a row and writing down all your work and keeping things in order, this is a piece of cake. Okay? So I'm looking at a few of you, and you know, like this is where it gets real. You're not sunk. You're absolutely not sunk. What this will do for you, and I'll tell you what this did for me, teaching it improved my ability to leave myself a good breadcrumb trail. In computer programming, because I get this over dinner at conversation, they talk about breadcrumb trails, having a path to get back to where you were and also find your mistakes along the way. And the kind of problems we're going to do right now reward leaving yourself a good breadcrumb trail, and teaching this improved my ability to do that for myself, because I was not somebody who wrote everything down. I wrote nothing down. I was a complete pain in the butt. If I was in my own physics class, I would slap me if I was 16 and doing what I did. Anyway, what we're going to start doing is non-perpendicular vectors. Okay, this is really easy. It's easy to figure out the resultant here. Why? Perpendicular! Those are at right angles, which means we can use Pythagoras, and we love Pythagoras. We've been doing Pythagoras for a long time. So we can figure this out algebraically. We can also draw it out graphically and check ourselves. But what about the kind of problems that we started off with, where we have things like airplanes, taxiing down runways, and then doing that, and our resultant vector is there? Huh. You don't say. We can solve that graphically. We know how to solve that graphically. We can make a scale, we can measure, but this is not a right angle. It's actually some weird obtuse angle. So how can we solve a non-perpendicular vector algebraically? Well, it's a combination of things, and a lot of it is trig. And let's walk through the basic theory on this. And we're going to start off with one like this that is an airplane taking off, because they're easier. The one the book throws out as your first example is way more difficult. So I want to start with the easy case and then move to the crazy case. Okay, so we've got an airplane taxis 200 meters before taking off at 23 degrees above the horizon. After traveling for 55 meters at this heading, what's their displacement? So you're looking for a resultant vector. The first thing we want to do with any of these, even though we are not going to solve this graphically, we're going to solve it algebraically, the first thing we want to do is make a picture, because the picture helps you understand it and helps you see the whole situation. So I'm going to go ahead. Now remember, since we're not doing this graphically, we don't have to be real careful about making this to scale. We can kind of approximate the scale. We don't even have to measure anything if we don't want. So I've got displacement 1 is equal to 200.0 meters. And then we're taking off above the horizon, and this is displacement 2, and this is equal to 55.0 meters. And I know where my resultant is going to be. Resultants always connect to the what and the what? Tail of your first vector to the head of your last vector. And I don't have to worry a whole lot about making those lines match up perfectly or making anything perfect because I'm not going to solve this graphically. I'm going to solve it algebraically. So the basic theory behind this is that for every situation like this, that resultant vector, if we look carefully enough, actually is a right triangle. What? That's crazy. That's crazy. I know, but it's true. And that right triangle is made up of an overall x and an overall y displacement. So what we're looking at is triangles within triangles, and we can do this with multiple triangles. This is where that color coding comes in handy, and if you want to grab colored pencils, they're on the tall desk. If you're doing this on paper, it's really helpful. If you're doing it on Doceri, you have all the colors you could possibly ever want. So let me get rid of those last two lines that I just did. And let's look first at our initial displacement. Okay, so for D1, for any displacement, usually there's an x and a y component. D1 is easier than that. What's the x component of that initial displacement? 200. The whole thing is on the x-axis. There is no y component. So for D1, what we would call delta x1 equals 200.0 meters. For D1, what is delta y1? This is easy. It's 0. There's no y component at all. Okay, well that's easy enough. Now, and I forgot to put in our little angle there. Theta is 23.0 degrees. That's terrible, Moser. There. So for D2, we have a delta x2 and we have a delta y2. How do we find them? Trig! This is where if you struggle with seeing these, what I actually suggest you do is pull out that second displacement, and you can do this. And then you can make yourself a little sort of expanded version of that. Okay? So this is what you're looking at for D2. Now, you have this 23-degree angle here. I'm not paying attention to sig figs for that little jot. Here's delta x2. Here's delta y2. So we know we're going to use our trig functions with our resultant, which is the D2. So setting these, I'm going to kind of do that for a moment. And I'm going to revert to my old habit of going from this angle straight across. Sine is so, opposite over hypotenuse. My opposite is going to pertain to my y2. And I'll actually get rid of these for a moment. So I know that the sine of D2 is equal to the opposite, which is delta y2. Writing, Moser, geez Louise. Over D2. I'm sorry, did I write the sine of D2? Geez, Moser. Sine of theta is equal to delta y2 over D2. Does that make sense? We're going to practice another one of these together. Well, then I can solve for this because I know that the sine of theta times D2 is going to give me delta y2. So now I have that piece. I'm going to shrink this. I'm going to plug in my numbers. Sine of 23.0 degrees times 55.0 meters. What's the raw number? The question that was asked was, how do you know that angle's 23 when you're looking at that little triangle? Because you're looking at, and this is horribly messy, let me see if I can clean it up at all. What you're looking at is this vector, and we were told that that vector was at 23 above the horizon. So if I put a little line in there, that's a good question though, because that's the kind of question that people suddenly, they think they know what they're doing, and then they go, wait a minute, where'd that come from? So yeah, that's... Okay, so we've got our delta y2, and I'm going to shrink a few things here. And now we want to find our delta x2. So we know that if we look back here, the adjacent side to that 23-degree angle is our x. So the cosine of theta is equal to, is equal to delta x2 or adjacent over d2. So now it's a fairly easy matter to solve for delta x2. Cosine theta times d2 equals delta x2. Cosine of 23.0 degrees times 55.0 meters equals delta x2. So what's our raw number? You guys have
50.27767.
Yeah, 6277, etc. I'm already done with it. Okay, is our delta x2. Now comes the fun part. We're going to take our delta x1 and our delta x2 and combine them into our total x displacement. So I'm going to shrink this. You've of course saved all those numbers in the memory of your calculator. I'm going to kind of move this over here. I'm going to move and shrink that just for my own. And this is where I very often do sort of color code. So I'm going to say, well, that was a mistake. I'm going to make everything associated with D1 green. I'm going to make everything associated with D2 this pretty blue color. And you can break it down any way you want. And then all my resultant calculations I'll do in red. So what I know, if I change this to red, I know that this resultant, if I look at the overall triangle, that resultant is going to be equal to the square root of delta x total squared plus delta y total squared. And it's really helpful to write that for yourself. Helpful because as you're going back through all of this, it's nice to be able to look at your breadcrumb trail. Is that too messy? Hold on. Okay. Very often this is the first thing I write down, because here's what this reminds you. That you have to find delta x total and delta y total. And I sometimes will get really crazy and use 5 different colors. So I'm going to say that delta x total equals delta x1 plus delta x2. Okay. And if you want those in purple, there is delta x1, there is delta x2. So it's the total x displacement. Well, I just happen to have those numbers. So delta x total equals, I'm going to pull this number, 200.0 meters plus this. What is it? 50.627 blah 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 meters. And it's really important to keep all those digits, of course, keep them on your calculator. So that plus 200, I get a delta x total of 250.627 blah 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 meters. Okay, great. I'm getting this total x displacement. How far on the x-axis they traveled from start. Well, I also need to get delta y. So I know that my delta y total is going to equal delta y1 plus delta y2. Well, this one's really easy, because if you look at that, that one's 0. So all of my y displacement happens in that second leg of travel. So I'm going to take this number, and delta y total is just simply equal to 21.49 blah 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 meters. Okay, cool. I have my total x and y transit. Now what I'm ready to do is make this final triangle. And I tend to do this visually. So I have here my delta x total, 250.62 blah 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 meters. I have my delta y total, my, what was it, 21.49 blah 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 meters. And I know that my resultant is going to go from there to there. So I can do the algebra at this point. I know this seems like a lot of work. It is a lot. This is tedious. It isn't hard. It's tedious. It's nitpicky and it's detail. But that level of attention to detail does pay off. So let's go ahead and I'll write out this final calculation. Okay, so I've got 250.62 etc. squared plus 21.49 etc. squared, square root thereof. I get a resultant value of 251.547 blah 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 blah. How many of you have the same raw answer? Good. Now, we're not done. What do we still need to do? Heading. You cannot have a vector without a heading, ever. Even if it's just straight east, north, west, south, left. You have to have a heading. So here, our vector heading, we're going to get by using, what can we use? Tangent. Actually, I mean, in point of fact, we could use any of the three trig functions because we have all three sides of the triangle. Traditionally, we use tangent to get that heading because it's the one that, it's got the least, there are a lot of steps folded in here. This has the least number of steps, so it's the lowest potential for error. Okay, I'm going to shrink a bunch of stuff. Okay, so we know that our theta is going to equal the inverse tangent function of delta y total over delta x total. Okay, so we plug in our values for our tangent function. We've already got them in our calculator. We just have to go up and find them. Okay, what do you get for a raw value for the heading? What are you getting? Give me a raw number. Theta equals? 74.6237. You have the complement. I think you put in your x and y backwards. Okay. And that's a common mistake to make. You got to be really careful with that. Okay, so your y should be in the numerator, x should be in the denominator. What do you get for your raw value? 4.900836664. Okay, and I'm getting 0.0869868 degrees. So we probably did a rounding thing. Yeah, yeah. Okay, so with sig figs, what would our final answer be for this question? Good grief, what an awful long way to go to get a single answer for a silly question. With sig figs, and we have what, 3 sig figs? 252 meters at 4.90 degrees above the horizon. So a hiker walks 25.5 kilometers from her base camp at 35 degrees south of east. On the second day, she walks 41 kilometers in a direction 65 degrees north of east, at which point she discovers a ranger's tower. Determine the magnitude and direction of her resultant displacement between her base camp and between the base camp and the ranger's tower. I think it's a little bit much to start with, but it does throw you right in on your head. So they have a whole problem-solving procedure for doing this. We can walk through this one together. I did assign 3 that are like this, and we'll probably, tomorrow's Friday, you have 1 period. We'll work on these and ask questions and fine-tune. Monday we'll probably have a non-perpendicular vectors FIP quiz. So let's just briefly get started with this. Where do you start? Drawing a picture. Always. This is super, super, super visual. So she is walking from base camp, and I'm gonna start off with all black lines because it's easy that way. She walks 35 degrees south of east. I'm going to draw myself a little compass rose up here. So south of east is going to be somewhere in this direction. Okay. So I know she's going, whoops, this way. And I know that, boy, that's a sloppy compass rose. This is why I do use graph paper, though I sometimes ignore it. So this is my 35-degree angle. And this is 25.5 kilometers. One nice thing about these problems, you don't have to do any conversions. You don't have to make this meters. As long as all your distances are in the same unit, you can leave them alone. It doesn't matter if it's, I don't know, pick a weird unit of measurement, whatever. It doesn't matter if it's, centimeters or picometers or terameters. As long as they're all the same, you can use it. So on my drawing, I've labeled the angle. I've labeled the displacement on that first vector. We're just waiting for it to show up on the screen. Hey, I screwed up. I usually don't screw up east and west. I usually only screw up left and right, but apparently it's an awesome day. So, yes, I put that going south of west. Let's fix that, shall we? Okay, I'm going to put in that. That looks more like a 45 to me. Remember, you don't have to be spot on about your angles and your measurements here, but it helps to be at least, close. Okay, so we've got our vector at 35 south of east now, moving 25.5 kilometers. Okay, we will finish this problem together tomorrow in class. If you can, start looking at those homework problems. Try one of them. See you tomorrow.